All right, so let's take a look at graphing the other trig function. So the sine and cosine are kind of the two main, basic ones, and then from there you can get into the other functions. So as a quick warm up here, let's think about the domain, the range, zeros, and then the period. So domain and range are going to be the same for both. So let's just kind of list those together. So for the domain for all of these things go on through all x values. So the domain is going to be all real numbers. Remember, they continue on forever. And the range is actually the same. If you think about which y values the parent functions are in between, it's always between 1 and -1, okay? Unless there are like transformations and whatnot, but for the parent function, between -1 and 1. The period is actually the same for both of these, right? It's going to take, you can see if we follow, like, for example, the sine curve, it does one full cycle, and it takes 2 pi. Okay, so 2 pi is like one time around the circle. That's when things start to repeat. That's what the period's talking about. All right, but where they do differ is they obviously have different, just different ordered pairs, different intercepts, and different zeros. Okay, so let's kind of list those because we're going to be using those zeros to help with the other functions. So for sine of x, we can see, maybe we'll highlight the zeros for sine of x. So the zeros for sine is the black curve here. So of course it starts at 0, then it gets back to 0 at pi, at 2 pi, and we continue on also in the negative direction. So the zeros are every multiple of pi. Okay, so sometimes you might see that written as like k times pi, where k is an integer. Just to get a little fancy here, right? It could happen at 1 pi, 2 pi, 3 pi, any whole number multiple of pi, so k pi. While for cosine x, the green graph, we see that its zeros occur at different spots. So what we could do, we could say it starts out at, the first one is at pi over 2, and then the next one will occur pi later, okay, or pi before that. So it could be written as pi over 2 plus k pi, where again k is an integer. Okay, and that's just a fancy way, so we don't have to list them all. It's just kind of a way of showing the pattern. Like it's gonna, the first one's gonna be at pi over 2, or not necessarily the first one, but the first positive one is at pi over 2. And then every time you add a multiple of pi, or subtract, I guess we could do plus or minus, you're going to end up with a 0. Okay, what we're going to need is to just kind of know how to graph them and sketch them out, and then use those to actually get the graphs of the ones we're going to do today are secant and cosecant. So let's take a look at what those look like. Okay, so when we think about secant and cosecant and even cotangent, which we will look at another time, just got to remember those are just reciprocals of the main functions, right? Secant is just the reciprocal, or 1 over cosine, while cosecant is the reciprocal, or 1 over sine. When we get to cotangent later, two ways to think of that. Tangent, cotangent, I mean, is either the reciprocal of tangent, 1 over tangent, or it could be thought of as cosine over sine, because tangent, remember, is sine over cosine. So there's some relationships there that we will use with other things as well. Let's dig into a graph though. Let's say we want to think about what does the graph of y equals secant of x look like. Okay, so what I want to think about is that secant is really 1 over cosine x. Okay, so I'm going to suggest first step is to graph the regular old cosine, the one we've been doing for a while here. And we're going to kind of use that to help us out. Okay, so cosine of x, if you remember, we're going to set up the scale. The period is 2 pi. Okay, so that means this would be 1 pi. These are our standard x values along the unit circle. Okay, cosine, of course, starts out at 1 and then goes to its midline of 0, down to its minimum, comes back to 0 and back to 1, and that's going to kind of give us a little guide. Okay, and this is much like if we were doing transformations, we might graph the parent function first and then use that. So this is kind of like our first step. Now here's the deal with secant. Secant, we know, is 1 over cosine, right? So since it's a fraction technically, or could be thought of as a fraction, if you remember, whenever the denominator of a fraction is 0, that makes the whole fraction undefined. Okay, so when cosine is 0, secant is actually undefined. And what we get when a graph is undefined is a vertical asymptote. Okay, so wherever cosine was 0, we're going to have an asymptote, a vertical asymptote for the secant graph. Okay, and then what ends up happening, we're just going to use the graph of cosine to figure out what the actual graphical part of secant looks like. Okay, and one way to think about it, think of all the points where cosine equals 1. Okay, the reciprocal of 1 is still 1. So secant's going to go through that point. The reciprocal of -1 is still -1. The reciprocal of that point is 1. Okay, and then it's another way just to kind of see where this is coming from a little bit. Let's just say, like for instance, that point right there, where the y value is 1/2. The reciprocal of 1/2 is 2. So if the purple, on the purple graph, if we're at 1/2, on secant we would be up at 2. Okay, and that would happen over here somewhere as well. And again, you don't have to worry about too much details. I just kind of want to show you where this is coming from, because this secant graph actually ends up looking like this kind of thing. You get these little, almost like parabola things. And as long as you just keep them within the asymptotes, it's just going to keep alternating back and forth, and you're just going to get all these weird looking, these graphs are weird, these little up and down parabolas. And that is actually what the graph of secant of x looks like. It's this guy, this guy, this guy, this guy. Okay, so as long as you have cosine graphed, get the asymptotes on there, and then you can kind of just use the key points, the maximum and minimums of the cosine graph to become like the little vertices kind of the parabolas. These are not really parabolas, but they're similar looking. That's how you're going to get the secant graph. Okay, similar process to do cosecant. If you recognize that cosecant is really just 1 over the sine of x, okay, and let's graph the sine of x first, and then we will just follow. It's very similar. Okay, so sine of x, 1, 2, 3, 4. We get our standard 2 pi period here. Okay, regular old sine curve. We'll do that one in yellow here. Sine's going to start out at 0, go to its maximum, midline, minimum, back. Okay, it's going to do one of these kind of things here. It'll keep going, of course, in both directions. All right, so it has asymptotes. Okay, the cosecant's going to have asymptotes where sine is 0. So right here at pi, right here at 2 pi, right? It's going to have asymptotes basically at every multiple of pi. Another one over here. So the cosecant graph, we'll do in red for our final answer, okay, is going to do the same thing. It's going to be those up and down little U parabola looking things, and they're just going to start at the mins and maxes of where the sine graph is. Okay, and again, we're not expecting perfection graphing these by hand. Just keep them within the asymptotes, keep the mins and maxes where the mins and maxes of sines would be, and that's kind of it. Okay, these graphs, not gonna lie, not overly useful. You know, if there's ever a problem when you're having to deal something with a cosecant graph or a cosecant function, you can always just turn it into a sine function with its reciprocal and then kind of use that to solve it. But they do exist and they are out there. I just want to make sure we kind of know what they look like. Okay, so to take care of one or to graph one with a transformation in there, we're just going to do the same kind of process, and we're going to graph as if it were a cosine graph for this one, because this is going to be 2 secant, so it's really going to be 2 times 1 over the cosine of pi x. Okay, so what we're going to do first is graph the cosine of pi x. Okay, we're going to see what it looks like, allow us to set up the asymptotes and whatnot based on that function, and then just do the little up and down parabola looking things, and that'll be it. So this one, if we set up the scale, this one does have a b value here, so the period's going to change, right? The period, instead of being the standard 2 pi, we need to always divide by whatever the b value is. So in this case, that's pi. So our period here is going to be 2. So we have 1, 2, 3, 4. That's going to be a 2. So we're looking at 0.5, 1, and 1.5 for our x values. Okay, we do have the amplitude of 2 going on here, the vertical stretch. So let's do our cosine graph based on that. Okay, so cosine is going to, I'm going to do this lightly, going to start out at its maximum, like cosine always does. And it's going to follow this pattern here, like a normal cosine curve. Okay, there's our standard, there's our 2 cosine of pi x. That means that we will have asymptotes on our graph whenever this thing is touching 0. So here. Okay, and then our final will look like, if we just choose a cool color here, if we want to do this in purple, the final answer will just have our little parabola looking thingies staying within the asymptotes using the little max and mins from the yellow graph, the cosine graph. And that is it. Pretty cool stuff. All right.